So today I'm just going to go over another project highlight, which happens to be very pertinent to what we've been talking about the last two lecture days, because this project is all about controls, 100% controls scope of work at this building. So it just so happens to be another Spokane Transit Authority building, um, which the other one was the maintenance garage that we talked about a few weeks back. But this time we are looking at the STA Plaza, which is downtown. So you've probably driven by this building a ton of times. Maybe you've even been there, but this is essentially their central hub downtown that all of the buses go in and out of. About 68,000 square feet, multi-level. I think it's a two-story with a below-grade parking garage. It's mostly big, open, common space. So you walk into the front door, and it has very high ceilings, some second level spaces, and some businesses. Like I think there's a Subway sandwich shop, for example, on the first floor. They needed all new DDC controls for all the HVAC equipment that they had. So as a reminder, DDC, that's the high end of the controls offerings that we talked about. So that is where they get a centralized front end where they can look at all of their equipment on a computer screen. They can look at the the status of equipment, see what temperatures are being read. They can change schedules and set points and all of that good stuff. They had an existing DDC system, but it was about 20 years old. And in the DDC world, that is essentially ancient technology. Within this building, they had a lot of different system types. So they had constant volume multi-zone units. They had single zone. Uh, we call them packaged gas DX rooftop units. It's essentially a unit that sits up on the roof. You can kind of see them just barely, a few of them in a row here, where everything is packaged into one box, essentially, and they have a gas furnace to provide heating, and they have a DX air conditioner to provide cooling. But each one of those is a single zone unit, meaning that it just serves one tenant space on that floor. They had a handful of water source heat pumps and some single zone hot water and chilled water units, just some very small hot and chilled water air handling units that served some specific spaces, a hot and chilled water plant. So they had multiple boilers, hot water pumps, at least one chiller, and it was a water source chiller, meaning it's attached to a cooling tower up on the roof, which you can see right there. And the hot and chilled water plants are actually in the basement, meaning they had to pipe from the basement all the way to the roof to connect those pieces of equipment, and then cooling towers, which I talked about. The project scope, the main driver here was they wanted new controls. They didn't have a lot of budget for replacing a lot of this equipment. All they really wanted was controls. And this was almost an afterthought. We were hired to do some audits at some of their other buildings. Actually, I think that maintenance garage was one of those buildings we were being hired to do an energy audit on. And this controls upgrade at the Plaza kind of came up just secondhand, and we chased it down, and it turned out to be a really good project that we were able to execute at the same time. But the bottom line, we weren't doing big equipment replacements. All we were doing was taking control of what was already there. So saving energy in this case, that was a nice bonus. Primarily, They just wanted that better control. And we're going to see that saving energy here was actually a pretty nice bonus. So some of the existing operating parameters. So this is how it was when we found the building. These are the baseline conditions. I mentioned they have constant volume multi-zone units. And if you recall, constant volume multi-zone units always have lots of simultaneous heating and cooling. Because they're blending the hot and the cold air all the time, you're just constantly having those two systems fight each other. The other thing we discovered, for some reason, these multi-zone units were designed for an extremely high amount of outside air, about 53% of their total supply air. If we were doing this design from scratch, we probably, well, we didn't do the calculation, but I suspect it would be closer to probably 25 to 30%. So probably half of what they were actually providing. And we talked to the client, and they couldn't think of any good reason why they were bringing in so much outside air into this building, which we know takes a lot of energy to condition. And these were designed to provide constant ventilation air, so a constant amount of CFM whenever those multi-zone units are on. So all the time they're providing 53% outside air, which is a lot. And all of their equipment was running 24/7. And I mentioned if I hear this, that they're running their equipment 24/7, that's when I really perk up and start thinking, oh man, there could be some really good opportunity here to save some energy. Their space temperature set points. So the temperatures at which they're maintaining within the building were all over the place. So there was no consistency at all. And in some cases, you could have some pieces of equipment in one area of the building with much higher or lower set points than in adjacent space, and you could end up with those spaces fighting each other because no zone is truly uh, in isolation. There's always some communication and transfer of heating energy within that building. So the baseline EUI was 212, which is massive. That is extremely high. What we proposed to do, and what we did do, well, I already mentioned they want new DDC controls on all their equipment. We implemented a consistent temperature set point, set of temperature set points throughout the building. So we worked with the client and they told us, well, we want to maintain our building at 72 in the summer. And then when we're unoccupied in the summer, let it warm up to 82. And then 67 in heating mode. If we're in unoccupied heating, 60 degrees. And it should be noted, these temperatures on the cooling and heating side are a bit lower than normal. Normally, we do an occupied heating set point of about 70 degrees. But in this type of facility, you think of all these people coming into the building to wait for their bus. They're wearing their outside clothes, meaning they're wearing coats and hats and gloves, and that all plays into the comfort of the building. And so it's not unheard of to maintain the building at a lower temperature if you're expecting the occupants to be wearing bulkier clothes. And then, of course, we have a 5-degree dead band between these two systems, where if we're between 67 and 72, nothing should be going on. We also implemented an occupied, unoccupied schedule. So remember, with these multi-zone units, specifically constant volume multi-zone units, when those are running 24/7, they are still using a ton of energy to blend that hot and cold air to make neutral air. When we're in those unoccupied periods, we probably don't need a lot of heating or cooling, but if the units are running, that means they're just providing neutral air. But to achieve that, with this type of system, they're taking cold air and hot air, spending energy to condition both of those, mixing them together to get plain neutral air. So it still takes a ton of energy. So instead, we're going to implement this schedule. So 5:30 to 11, Monday through Friday, 6:30 to 9 on Saturday, 7 to 7 on Sunday, because that is when the plaza is actually open. The other thing we did is we implemented demand control ventilation. So now we're still going to allow the system to provide lots of outside air. It was designed for 53%, and it is still capable of providing 53% outside air. But with this logic, it's only going to do that if the space CO2 levels actually say we need that much ventilation. And maybe the original engineers had a very good reason for designing it for such a high outside air. But by putting in demand control ventilation, we can heavily trim that back whenever we don't need that much. So the other reason I thought this would be a good project to talk about is this gives me a chance to talk about whole building energy simulations. So this was outside of the scope of this class. When I was first developing this class, I really wanted to have a module where we talked about this and actually got to use one of these programs. But to use the program, you really need to have a solid understanding of all of these system types before you even set foot in the software. And it ended up just being too much. But here I can at least give you a glimpse of what it looks like when we get into whole building energy simulations. So this is what the building looks like from Google Earth. And then this is the eQuest model that I created to do my energy savings calculations. So it's a pretty decent match. And you can see this green area down here. So that's the parking garage down in the basement that you can't see in this view. So I used the program eQuest to create this entire building to run my simulations. So I created a model that not only has all the building structure components, all the walls and the roof and what those are constructed out of based on U values, assumed infiltrations, and then I also have to create all of the mechanical systems. So I had to create systems for the multi-zone air handlers, the heat pumps, the rooftop units, all of that stuff has to go into that model. The first step in making this model is we have to create a baseline model. And the intent of the baseline model is to create a energy model that mimics what is going on in that building today. So try to make a one-for-one recreation. So what we do is we go out there, we actually look at the systems, we talk to the owner, we find out when are you running these systems, and they say, oh, we're running them 24/7. Well, that's really important to know for our model. We also ask questions about set points. We spend a lot of time looking at the old drawings for the building that show all of this equipment on the plans and how the ductwork is routed through the building and which systems serve which areas of the building. It takes a lot of effort to create that baseline model. The other piece is we need to get their actual build energy use. So we will get the gas bills and the electric bills for that building. And now we have two pieces of data, or well, I guess more than that, but what we can start to do is try to run simulations with this baseline model until the simulation output starts to match what the bills actually said. So that's this next step. If we look at the electricity consumption, so the blue line here, that is their actual electric use. The red line, or excuse me, the dashed black line, that's what my model is saying the energy use is, according to my simulation. And then we have a spreadsheet, that's the red line, that will do some weather normalization. Because remember, if you're looking at that build data, you can look at the heating and cooling degree days. You can look at the weather severity for when that build data happened. But when you get into the energy simulation, you can't just plug in that same weather data. What happens is eQuest has a weather file that is representative of Spokane, and that's not going to 100% line up with what those bills actually saw. And so we have to do some of that normalization. In this case, you can see some of these months are pretty far off. I mean, especially in the summer here, I am peaking much higher, but then I'm dropping below. And this is pretty normal. It can be pretty challenging sometimes to try to tune these to get your model to line up with their actual build use. You can also run into issues where what if their electric and gas meter gets read on the middle of the month and not the start or the end of the month? So when you look at the bills for February, that could be from January 15th to February 15th. So you're now actually straddling the line, and it's going to be harder to tune your model based on that awkward split. On the demand side, it's reasonably closer. On the demand side, we don't do any normalization because this is all peak demand for each of these months, and you can't necessarily correlate that to heating and cooling degree days. So we don't do any normalization on the demand. It's also notoriously much harder to tune. I'm actually pretty happy with how this one turned out. This is one of the better ones. Usually demand is much harder to align with the bills. And then we had our gas use. And this we do try to normalize. So the blue line, again, that's their actual gas use. And I suspect it kind of looks like everything is shifted a little bit to the right. I mean, I would expect the bottom of the peak here to be more in June, July, rather than August. So there could be some funny business going on with when the meters were actually read. But you can see I have some of the same challenges where some of these months are pretty far off. And that's okay. That's totally expected. What I do want to get pretty close, I know this is a lot of numbers, but let's walk through it. So in orange here, we have our actual weather data. So this is actual heating and cooling degree days I pulled out of Weather Data Depot, which is a website you had to use on one of your homeworks. Here are their actual utility bills for kilowatt hours, kilowatts, therms. Then in green, this is what my eQuest model output. So we have the eQuest weather data based on whatever weather file they have for Spokane. And you can see on the cooling degree days, 723 versus our actual of 1,106. There's a pretty good discrepancy there. And then on the heating side, about 5,200 versus 4,800. There's a discrepancy there as well. So this green right here, this is the what I call the raw outputs. So this is non-normalized data. So you can see our kilowatt hours is a little bit low relative to our actual, and our gas use is a little high compared to our actual. But if you look at the weather data, that kind of makes sense. So then here we take that eQuest model and we normalize it based on this actual weather data. So we're taking the eQuest data and normalizing it to the actual data. And now our normalized values right here, you can see individual months are pretty far off on the electric and gas difference, but my overall for the year are within 1.5%, which I consider anything within 3 to 4% would be acceptable. So I would consider this a win. Even though some of my months, individual months, are pretty far off, my total over the year is still pretty close, extremely close. So that's creating the baseline. So now I have this version of a model that more or less mimics what is there today. And that's the hard part. That takes the bulk of the work. From here, I create a new version of the model where now we get to play with, well, what are we going to be doing? What are the changes we're going to make? So we would go into the model and implement those controls related changes. So we would implement demand control ventilation. We would put in consistent set points and our scheduling and anything else we're doing. And then we run the simulation again. And that gives us this delta. Our blue line is our baseline model. And then our green line for our controls upgrade version of the model, you can see there's a pretty consistent delta pretty much year round. And that would be our savings. On the gas side, the same thing. And you can see, that is a drastic reduction in gas use. And that is virtually entirely owed to that demand control ventilation strategy to reduce the outside air based on the CO2 levels in the space. So the summary, at the end of the day, how do we do? Our baseline data, they used about 1.6 million kilowatt hours per year, 88,000 therms per year. I mentioned an EUI of 212, which is extremely high. And they're spending a little over $200,000 per year on their utility bills. When we're done, we dropped their electric use to about 1.4 million kilowatt hours. So that's about 15% savings. That's not bad, but 15%, that's not going to make anyone's jaw hit the floor. On the gas use, however, we dropped their use down to 46,000 therms per year. We saved almost half of their gas bill. And that's almost entirely owed to that demand control ventilation strategy. Well, it's not entirely true. A good chunk of that is probably also attributed to implementing a schedule and turning off those multi-zone units, especially during those unoccupied hours. Their new EUI is around 137, or about 35% savings. That's pretty dang good. And at the end of the day, their new bill is around 172,000 a year, and we save them about $40,000 per year, about 19%. Total cost of this project was around $235,000. In the construction world, at least in the commercial construction world, that's not a big project. I think the maintenance garage project we looked at was something like 1.6 or $2 million, somewhere in that ballpark. So potentially, 8 or 9 times as much as this. But this was strictly controls, which tends to be a lower cost retrofit. I mean, it's still a good amount of money, but in the grand scheme of things, compared to other retrofit projects, that's a small dollar value. And we got a nice, well, I say we helped them get a nice utility incentive from Avista. We showed them how much energy we were saving, and they wrote a check to STA for $78,000. And this would be an example of a custom incentive. So when we went and we called Avista and we said, this is the project we're going to do, they said, all right, that sounds great. We know everything you described is going to save energy, but it doesn't fit into any one of our usual buckets, one of our usual programs that we offer. So we are going to require you to do your install, tell us when to start the clock, and then a year later, we will look at their bills and see if you actually saved what you said you're going to save. And we did. So they had to wait a full year to get that, but they got it. And that knocked a good chunk off of their cost. So 150,000 ish per year. And we saved them about $40,000 per year. So that gives a simple payback of a little under 4 years. And that is an extremely good payback. Very few projects I've worked on have a payback less than 5 years, or even 10 years. 10 years would be a very good payback. So I mentioned this. This is all very pertinent to our discussions on controls. So to supplement this, I wanted to show you what a set of design documents would look like for a project like this. So this was the mechanical design package that we produced. So I was a lead design engineer on this. So I guess let's just walk through it. The cover sheet, a lot of words, but this basically just acts as a legend, tells you what all these symbols and accessory, or excuse me, abbreviations stand for in the drawing set. Little vicinity map to show where we are at. Sheet index to tell you all the beautiful sheets you have in this drawing set. And then this is a very important part of it. It's what's called the basis of design. And this acts essentially as a narrative for what we are doing and helps describe any major design decisions that were made. The idea is that if an engineer were to pick up this drawing set 10 or 20 years down the road, they could read through this document and get in the head of our engineers and understand what we were thinking. And this is not something you see on a lot of drawings, but it's something that we put on every single engineering set we put out. So it's very important. Also helps us to say, well, the reason we did this is because the owner wanted us to. Sometimes we have to do things that are not necessarily something we would recommend to a client. Now, we're not breaking any laws, we're not doing anything unethical, but we could be putting in a system that could potentially have some comfort issues in certain areas during certain times of the year, and to fix it would cost a lot of money. And so we would recommend to the client, hey, this is what you should do to do it right. And the client might say, well, that sounds great, but I don't have the money to do that. So this is the way we're going to do it. And we, as their consultant, would say, okay, that's great, but I'm going to note it here. Owner direction. You told me this is what you wanted, so that I don't have an engineer down the road looking at my drawing set and saying, man, this Derek Larson guy, he didn't know what he was doing. So these next sheets, this is where the bulk of the design work went into this project. These are all of the controls sheets. So we have a rough schematic here that describes all of the equipment in the building. So we have all of this gets connected by a Cat5 cable to get to the owner's network. You have a building level controller that is essentially the brains of the entire operation. And then you have your individual unit controllers. So we have 7 of these units. We have 6 water source heat pumps. We have 4 big multi-zone units. And it just kind of gives a representation of the hierarchy of everything on the project and everything that the control system has to pick up. And then you get into the specific equipment. So this is a water source heat pump. So we have our compressor in the unit, our fan, our DX refrigerant coil, a filter, return air coming back, outside air coming in. In this case, it was fed directly from a direct outside air system, a DOAS. Our condenser water coming in and out. So that's all the parts and pieces. And then you have to turn your head 90 degrees to read this, but these are all the control points. So for example, this supply fan start stop. This is a digital output. This is a binary signal from the DDC controller, which is represented by this box. So this will send a signal out to the unit to tell this fan to run. Then we have the compressor enable. Similarly, send a signal out to the unit, tell the compressor to turn on. So this is how we're controlling this equipment. We also have a bunch of monitoring points, these TE with the circles. That's a temperature element. So this is plugged into the supply air. So we can see what is our supply air coming out of this unit. This IS is a current switch. So that will tell us when the compressor is running. What that allows us to do is if we are sending the compressor enable signal, if we're telling the compressor to run, well, that should tell us it's running. If we're telling it to run and it tells us it's not running, well, now we can alarm and say, well, we got a problem here. So I won't cover everything, but you have your thermostat. The idea is you just see all kinds of stuff here where we are either sending signals out to tell this equipment what to do, or we're bringing signals back in, like this temperature reading is coming back into the unit as an input. In this case, you might notice some of these are a half tone, so they're kind of grayed out. Those were existing control points that were already there. So our main intent here was to replace this part in green, disconnect all these wires, put in a new controller and reconnect those wires. But on our recommendation, we added these darker control points. So they didn't have a fan status point before, and we added that point as part of this project. Then you get into the sequence of operation. And this is essentially a narrative description of how this thing is supposed to run. So you can see here, under the general, each heat pump shall operate in any one of 4 modes. Well, you know what morning warm up, morning cool down, occupied and unoccupied mode all mean. And those are the 4 modes this could be running in. And when we're in occupied mode, here's what should happen. Here's what the dampers should do. If we're in unoccupied mode, here's what should happen. Basically, everything should be off, unless the zone temperature falls outside of those unoccupied set points. Then we need to tell it what to do. morning warm up and cool down. We describe what needs to happen there. And then all of the alarms we want to see. So this reads kind of like programming language, but we're not the programmers. So I would give this sequence to the controls provider, and they would handle all of the actual programming to make sure that my intent as the engineer is what is actually implemented. Then you get to multi-zone unit. So you can see there's a lot more going on here. But at the end of the day, we have our common supply fan, we have a chilled water coil and a hot water coil. And then we have our common actuator that's blending a bunch of cold and hot air streams. So we show one of these as kind of a representative. And if we follow that wire back, keynote 1, well, what does keynote 1 say? So there'd be 6 of those dampers on that one unit. And then more narrative description of what's going on. How's this thing supposed to run? We have a small DOAS unit and a condenser water plant. So we can see our cooling tower telling that basin pump when to turn on, also monitoring the status on the pump so we can tell when it's running, monitoring temperature. Yeah, I won't go over all these, but hopefully you get the idea. We're telling them what control points we need, and then also describing the sequence of how these things are supposed to operate. So these 3 sheets, I think 3 sheets, yeah, that's the bulk of the design on this project. Just putting new controls on existing equipment. After that, you get into the floor plans. In this particular project, there's not really a lot to show. All we're really showing is existing equipment locations. And if you looked at this keynote 1, it probably says something like provide new controls on existing equipment. So not terribly exciting. We do show where all the thermostats are, which is important. We don't want them to decide where to put those and then to have us go in later and say, well, why'd you put it there, dummy? It should go in this other room. Well, why didn't you tell me that? Yeah, just more of that. But this is what a controls design drawing set would look like. And doing controls is probably one of my more favorite things on what we do. I like to look at this equipment, think about which control points we want, because every single one of these that we add costs money. So you can't just ask for everything because you're going to end up with a very expensive system. So there is somewhat of a battle there in thinking of, well, what would add the most value to the client and what do we maybe not need? And then also writing these sequences of operations are kind of fun to do the logic, not really a puzzle, but just thinking logically about what needs to happen and also trying to think about all the possible scenarios that could happen to this unit and to write your control logic in a way that will cover you under all those scenarios. The last thing I was going to show you, might take me a second to open. Yep, hang tight. Okay. I just wanted to give you a quick overview on what the eQuest interface would look like. So this is the STA model. So we can look at this nice three-dimensional view, see what it all looks like, make sure our windows look correct. Um, this wall is all white because it meets up against another building, meaning there's no heat transfer associated with that side of the building because it's considered adjacent to a conditioned space. And the way we put in this data, well, there's two ways. The quick and dirty way is to use their wizard, which gives you a nice guided user interface to build your model. But the wizard does have some limitations. And so you can instead go into what they call detailed mode, which is an absolute nightmare to work in. And I try to stay within the wizard mode unless absolutely necessary. But the two main parts of this, the part right here is our building shell. So this would be everything associated with the envelope of the building. So the actual physical construction. And the construction of the building itself has nothing to do with the HVAC systems. But here's where I draw out my footprint. I draw out my zones. So wherever you see these dividing lines would be considered a different zone. And I can say, well, maybe this room right here is a conference room. And this tenant space over here is that subway where they have all kinds of cooking equipment. You can define how it's constructed. So what are your walls built out of? What's your ground floor? In this case, this floor is over a parking garage. But I could say instead that it has earth contact. Ceilings and walls, I'll kind of skim over some of this stuff. Windows, usually the easy way, rather than just plugging in every specific window, we just put in a percent. So 15.7% of our south-facing windows, or excuse me, 15.7% of our south-facing walls are window. You can see you have a lot more glass on the north side. We have a building schedule. So when is the building occupied? Which could be different than when is the HVAC running. Because just because the HVAC is running 24/7 doesn't mean the building is occupied 24/7. And you can actually see an occupancy profile kind of throughout the day. So they're assuming, peak in the morning, peak in the afternoon, kind of a drop off around lunchtime. And they do similar profiles for things like lighting and miscellaneous loads like computers and things like that. Here you can define what types of spaces you have. So what spaces are offices versus corridors, restrooms, conference rooms, and then also which HVAC system each of those spaces happens to be on. You can plug in some lighting, watts per square foot loads, and they have some defaults built in for these various space types because sometimes you don't really know. And sometimes you just have to do a best guess. So that's the bulk of the shell. And you can see I had to build a different shell for some different parts of the building. So this model you're looking at is actually 5 different shell components that are kind of pieced together. And then you have all of your HVAC systems. So if we go into the multi-zone, I can define things like what's my cooling source? Well, it's a chilled water coil. What's my heating source? It's a hot water coil. Um, and then what type of system do I have? So we have all these different options. In this case, it's a multi-zone air handler. I can plug in my space temperature set points for occupied and unoccupied. And this program also has the ability to give different seasons. Like if I had a school, I could set up a summer schedule and a school in session schedule, which would give me 2 rows of set points that I could work with. Fan information. What's my brake horsepower? How much CFM am I doing? What's my fan type? In this case, they had variable speed drives on there, but we could have some inlet vanes or discharge dampers. And eQuest has some built-in energy curves. I don't know if that's the right term, but if I select discharge dampers or inlet guide vanes, eQuest has some built-in formulas to account for the energy use with those technologies, as opposed to a variable speed drive. And then we have the schedules. So this would be, when is the HVAC running? In this case, it's on 24 hours a day. And I create one of those for all the different system types in this building, which you can see is quite a lot. And then I can get into my chilled water and hot water plant equipment. And so here I can define a whole bunch of stuff about my chilled water system. Most important one being, what is my chiller efficiency in kW per ton? And that is at an AHRI certified condition. But if I plug in 0.6, eQuest is smart enough, or has the built-in tools to estimate a varying efficiency based on the varying conditions that you might see over a year. We also have info on where the project's at. So I mean, that's a very important one. So I have this Spokane International Airport weather file that I've loaded in, because this building would operate very differently in Spokane versus Arizona. So pretty important to dial in. So that's a very quick rundown of eQuest, just to give you a glimpse of what full building energy modeling looks like. There are more advanced tools that they use now. The downside to eQuest, well, I'll start with the upside first. The upside to eQuest is it's free. Anyone can download it. The downside is that because it's a free product, there is no official support for it. And so if you run into a problem or a quirk or a bug, your only recourse is to find the eQuest forums and user groups online to find other people who are just as miserable as you and have found the solution to whatever problem you're having. And this program, I started using this program in 2011, the very start of 2011. And now we're 10 years later, and there really haven't been any substantial updates or improvements on it. So some of the newer system types, like VRF systems, for example, there's no explicit way to model VRF using eQuest. But there are some more advanced programs out there that are doing similar things, just in a different interface and with more capability, but those tend to be paid programs. And McKinstry as a whole, we've been shifting away from eQuest and using one of the better options that we actually spend money to get that support when we need it. But there still are a lot of projects that are going to use a program like eQuest. All right. That is all I had for you. Any questions on that? All right. I will stick around for 20 minutes or so if there's any homework questions. Otherwise, you're free to go, and I'll hopefully see you Thursday.